Okay, so kinetic friction is friction of objects that are in motion. Our kinetic friction depends on the surfaces that we're looking at, and there's different what we call coefficients of friction based on what the types of surfaces are. And we're looking at it in comparison to the normal force. Okay, so here's our equation for the force of friction. Now we have another equation that we can substitute into our F net equation, to our overall. And this is force of friction is equal to get a different color. Force of friction is equal to a Greek letter called mu times the normal force. This subscript here with the K just means kinetic. Okay, coefficients of friction, there's different coefficients of friction for kinetic and static friction, which we're going to see here in just a second. But overall, your force for friction, your equation stays the same. Okay, so force of friction is equal to coefficient of friction, which is this mu letter, times the normal force. Okay, so to kind of display this thought of a friction being applied proportional to the normal force, I want you to take your hand and just rest your hand on the table in front of you. Okay, rest it very lightly. Okay, then I want you to attempt to slide your hand forward. Difficult, easy? What do you think? Depends on how clammy your hands are, right? Okay, relatively easy. Now if you exert a force, if you push down, what happens to the normal force? Does the normal force increase or decrease? Increases. Is it harder for you to push your hand as you increase your force you're applying to the table? Yes. The normal force increases, which means the frictional force increases. Okay, so the more pressure that you apply to that surface, the harder it is for it to start moving. Okay, that's why it's harder to get larger objects started moving, things like that, because they're exerting a greater normal force. Okay? So now let's talk about static friction. This is friction of an object when it's at rest. So to first get an object in motion, it has to overcome static friction. So we've got to overcome our static frictional force to put an object in motion. So when an object's at rest, it has static friction acting on it. When it's in motion, it has kinetic friction acting on it. Okay? As soon as it starts its path or it starts in motion, then it has kinetic friction. When it's at rest, we've got static friction. The equation overall doesn't change, but we think of the maximum frictional force as being when something is at rest, right? You have to overcome that frictional force. So your book labels it F max. I'll still call it just F sub F for regular friction. Okay, nothing changes here with our overall equation, but this mu sub S means static coefficient, whereas mu sub K means kinetic coefficient. Okay. Not anything you really need to know the difference between. You will always either be given those coefficients or you'll solve for them or something like that. Coefficients have no unit. So the coefficient of friction, this mu character, has no unit. It's just a number. And each type of surface has been assigned a coefficient of friction. Okay, so go ahead and turn to page 96, and I want you to read that last paragraph here about. Okay, so between these two, the coefficient of static friction or the coefficient of kinetic friction, which of those is typically going to be a larger value? Static friction will have a larger value. The coefficient of static friction will usually have a larger value. That's because it's harder to get things started, right? It's harder to get an object put in motion as opposed to just keeping it in motion at a certain velocity. Okay, so if you look on page 97, table 4-2 has this table of coefficients of friction, and you can compare these two coefficients. The first column is static friction, the second column is coefficient of kinetic friction, and you'll notice that static is always larger. Okay, some of them get very, very near frictionless, which gives us a very, very small margin of difference. Like you'll see those synovial joints down at the bottom. There's hardly any friction within our joints, right? So even though these two values say they're numerically the same, static would still be a little larger. Okay, these only take it to the hundreds place. But otherwise, you'll see the coefficient of static friction is most of the time larger. More often than not, our coefficients of friction will be less than 1. Okay, you'll get coefficients maybe in the, like this one says rubber on other wood solid surfaces, 1 to 4 range. I usually see coefficients of less than 1. Okay, so when you're solving for the coefficient of a friction, if you get numbers like 45, you know you're way out of your realm here. Okay, so when we're talking about coefficients of friction, you should be looking for a very relatively small number between 0 and 1. Okay, that's just kind of a heads up thing for you to check your answers. Generally, we're looking at things less than 1. So get written down what you need to, and then we have to start with a free body diagram. We have to start with our net force equation. Okay, so for this overall, in our problem, our overall goal is to find the horizontal acceleration. But I'm going to walk you through every step that it takes for us to get there. Okay, so in order to find our overall goal of horizontal acceleration, we've got to do quite a few things to get there. Okay, so I'm kind of taking you through every step. There's certain steps you can, maybe skip over or do in a different order, obviously, but I'm going to take you through what the steps that it takes to get there. So let's start here with our free body diagram. So, Thomas, can you give me one of the forces, please? Okay, and it's going which direction? Downward. Okay, Jensen, can you give me one? Okay, friction, and it goes in which direction? Left. Okay. Brad, can you give me one? Okay, it goes in which direction? And Catriona, can you give me the last one? Good. All right, so here's our free body diagram. Our overall goal here is to be looking at the horizontal acceleration, which means in general we care about the horizontal forces, right? But what we need to know is our normal force, because that takes into our frictional force equation. So we have to work with both of them here. So we're going to walk through these steps to be able to calculate our overall horizontal acceleration. Okay, before we can do that, let's go ahead and write our net force equation in the horizontal direction. Okay, since we're looking at horizontal, we're going to take rightward forces minus left, which means we'll take force applied minus force of friction. Okay, that's what we're getting towards here. But let's go ahead and walk through the steps here. So finding the force due to gravity, we're solving for F sub g, which means we take what times what? Mass times gravity. So we're going to take 50 times 9.8. Okay, we've got our force due to gravity. What does that mean for our normal force here? What do we know about this acceleration in the vertical direction? Is our sled moving in the vertical direction at all? No, so what two things should be equal to each other? Gravitational force and the normal force. Those two should equal each other because it's not moving in the vertical direction. So that means our normal force is automatically just equal to 490 newtons, okay, because our object is not moving in the vertical direction. So now we're going to calculate F sub F, our force of friction, and we're going to take our coefficient times the normal force. This coefficient of friction was given to us in our problem, 0.01. So we'll take force of friction equals 0.01 times our normal force, which is 490. Which means our frictional force is small, 4.9 newtons. Okay, so now we can go back and start plugging things into our net force equation. Do we know force applied? Yeah, what is it? 75. Yeah, 75. We know our frictional force is 4.9. And what can we substitute in F net for? Mass times acceleration. Good. MA. We know our mass, which is 50. And we're solving here for acceleration. So we'll take 75 minus 4.9, get 70.1. Divide that answer by 50. And that gives us an acceleration that's equal to 1.4 meters per second squared. Okay, so now instead of just giving you a frictional force, you have the ability to solve for it. Okay, you've got to take into account the normal force, so you need to be looking at whether this object's accelerating in the vertical direction. If it's not accelerating in the vertical direction, you know that F sub g should equal F sub n. Okay, which will be an easy substitution for you to make. Then when we calculate our force, we're going to look at the coefficient, and we're going to find the frictional force to plug in there. Okay, you could have done all of this work just by basically plugging in numbers here, setting up our equation, and then plugging in this whole equation right into here before, instead of just solving for 4.9, right? You could have done it in one fell swoop in your equation, but I broke it down into individual steps. So that's up to you. If you can combine them into one bigger step, that's fine with me. You can just plug those things in, that's fine. I'm just breaking it down step by step so that we can see where all the numbers are coming from. Okay? Any questions here? All right. Okay, so start here with our free body diagram. This problem looks essentially the same as our last one. Okay, so we're going to go ahead and plug these into our F net equation. So we're going to have to go through the process of finding F sub g, finding F sub n, calculating our frictional force, doing all that kind of thing. We can do it all in one step if we really want, or close to one step. Okay, we do need to calculate F sub g. Okay, so take our mass times gravity. What do we know that F sub g should equal here? Not its value, but what other force should it equal? Fn. Good. It should equal F sub n. Okay, so here, if I want to go ahead and start doing substitutions into my main equation, I can take mass times acceleration equals force applied minus coefficient times the normal force. Okay, I can go ahead and do those substitutions into that equation if I want, instead of solving every single step individually. Okay, which means I can go ahead and plug in 225A equals 710 minus 0.02 times 2205. And it's not 0.02, it's 0.20. All right, Mary, what'd you have? 1.2. What's our units? Very good. All right, so this time our free body diagram looks a little bit different. We've still got our force due to gravity going straight down. We've still got our normal force going straight up. This time we've got 100 newtons at an angle of 40 degrees. Okay. And we've still got a frictional force. Does our frictional force go at an angle down like that? No. It needs to go parallel to the surface, so it needs to go straight to the left. Okay. So we're still going to walk through all of our steps here. Force due to gravity, or F sub g, we're going to find the normal force, frictional force, and our overall goal is to find the horizontal acceleration. Okay. So to find our normal force, what's one thing that we need to do? What's the first thing that we should do with this force at an angle? Yeah, we have to break it down into components. So we're going to find F applied y and F applied x. So to find F applied y, we'll take the hypotenuse times sine of 40. And to find F applied x, we'll take 100 cosine of 40. Are we going to need both of these components of our applied force? Yeah. We're going to need both of them. We need the force applied y to help us solve for the normal force, and we need force applied x because that's our force in the x direction. Okay? So we're going to take 100 times cosine of 40 and get 76.6. Okay, do we agree with both of the components there? All right. So let's go ahead and go about solving for this normal force and our force due to gravity. We can do it all in one step if we want. So what's our net force equation in the vertical direction? Upward force is minus downward, so F applied y plus the normal force minus gravitational force. Okay, is our object leaving the ground? Is it accelerating in the vertical direction? No, it's not, because it tells us it begins to slide. Sliding means it's staying on its surface. It's not leaving the ground. It's not accelerating in the vertical direction, which means F sub net in the vertical direction has to equal 0. Good. Okay, so F applied y we just solved for to be 64.3. The normal force is what we're solving for. And F sub g, we're going to take mass times gravity, so 30 times 9.8. Okay, so that means that F sub n should equal 229.7. Yeah? Okay. Okay, so I'm going to get rid of some of this work down here. So we've got our normal force. Now we can start looking at our horizontal forces, okay? Any questions as to how we found that normal force there? We know the box is only sliding. It's not moving in the vertical direction. It's not accelerating. That's why F sub net in the y direction is equal to 0. Now let's look at F sub net in the horizontal direction. We'll take F applied x minus our frictional force, because those are the only two forces that are acting in the x direction. Once we break down this 100 Newton force at 40 degrees, do we ever use the 100 again in a problem? No. Once we break down that vector that's at an angle, we never use it again in the problem. Okay, so don't ever plug that back in. Once we find its x and its y components, we're done with that angle, and we're only working with its x or its y components. Okay, so don't ever put that 100 back in anywhere. Okay, now we can do our substitutions here. So we'll take m times a equals force applied x, which we solved for, and we found it equals 76.6. Force of friction, we're going to take coefficient, which is 0.3, times the normal force, which is 229.7. Okay, and sorry, we can get rid of our mass here, and we're going to write 30, okay, because that's our mass. All right, Thomas, what'd you have? 0.26 meters per second squared. That's what I had.